Okay, so yeah, welcome back, everyone. Thanks for coming. I'm going to continue with this discussion of the basic existence and regularity properties for generalized Ricci flow. So like I said last time, I think if you're familiar with the basic parts of the story of the sort of PDE aspects of Ricci flow, there's really not anything terribly new at this stage yet that I'll cover. The theory is kind of more at the level of like the very general theory of Ricci flow regularity. But eventually we'll get to talking about like generalized Ricci flow in the complex setting, like pluriclosed flow and generalized Kähler Ricci flow, where we could say a lot more. But I'll mostly try to emphasize like some of the unique features present here. And so let me just maybe very briefly recall what we discussed last time. So these are the same slides as last time. So we have this generalized Ricci flow, a PDE, which we have at least these two faces for now. One is given classically in terms of a metric G and a two-form B, and then the three-form H. The two-form B is a potential for this three-form H as follows. And then the metric evolves by minus twice Ricci plus 1/2 H squared, where this H squared is this tensor we discussed before. And then B evolves by minus D star H. And then, like as Mario discussed, you can phrase this naturally in the language of generalized geometry by expressing it as a flow of generalized metrics on an exact Courant algebroid, flowing naturally by minus twice the Ricci tensor. So script G is an endomorphism of the tangent bundle, and so this is the sort of natural way to think about the evolution of G in terms of this generalized Ricci tensor. And then and then the point is these two formulations are equivalent. So maybe I won't review how that works. And then so last time we proved short time existence, where again the main issue is sort of gauge fixing. And the sort of main point is that, well, you sort of have an enlarged gauge group now coming from these automorphisms of the Courant algebroid, but those are exactly good enough to render the flow parabolic. And so using this sort of fairly well understood like gauge fixing or de Turck method, we proved this short time existence statement. So if you have initial data on some compact manifold, then you can always solve the flow at least for epsilon seconds. And I'll also skip the proof. So we discussed this last time. Maybe I'll just again mention some of these perhaps interesting things that have not been done yet. So in particular, establishing short time existence for complete manifolds with bounded initial curvature. Or maybe weaker hypotheses. So this was done for the Ricci flow by Xi, and requires fundamentally what sort of boils down to the proof from before, but you have to use like cutoff functions, and you need some more estimates to make it precise. Almost certainly this can be done, but has not been done rigorously. Also, there's these questions of backward uniqueness of solution. This was done for Ricci flow by Kochvar. And again, it's quite natural to expect that this is still true for generalized Ricci flow. It's quite a general idea, but this would prove stability of the isometry group at finite times.
What does it mean, stability of the isometry group?
Just that so basically what Kochvar proves is that for a smooth solution of Ricci flow on like a compact time interval, the isometry group does not change at all.
Okay.
So it's very easy to show that it doesn't shrink, that isometries are preserved. That sort of follows from the uniqueness. But then what he proves using this backwards uniqueness is that it doesn't enlarge. Of course, it's kind of, I mean, it's a bit miraculous, right? Because for all these for all these sphere theorems, right, you start with some metric on like the sphere with no symmetry. And then you converge, of course, to one with a nice large symmetry group. You converge to the round sphere, but it happens in like a singular way. Or alternatively, like when you normalize the flow, it happens at time infinity. It takes an infinite amount of time to like pick up these isometries. And then, sorry. Okay. Yeah, and then sort of a related question, Kochvar proves stability of the holonomy group along generalized Ricci flow. And I just sort of mentioned this to point out that, there's a much more basic question sort of still missing from the theory of generalized geometry, which is, well, there's probably many different holonomy groups you might imagine are relevant, like for instance, holonomy of the bismuth connection. But perhaps there's a notion that's more attuned to the theory of generalized connections and generalized curvature, which is more relevant for generalized Ricci flow. Actually this is a bit technical, but so in the proof of short time existence, you end up using this like harmonic map flow to sort of reconstruct the right family of diffeomorphisms to relate the standard Ricci flow with the gauge fixed Ricci flow, this de Turck, Ricci de Turck flow. And so actually we didn't work this out, although it would be relatively simple to do so. You could try a similar thing in solving for the GB flow directly, and probably the correct flow for the family of automorphisms that you need is probably the gradient flow of this like sigma model energy, this like modified sigma model energy. Because of course in the with the H field gone, this just is the harmonic map energy somehow. So maybe, I'm not sure, but right. And then so last time we spent a little bit of time discussing these basic regularity results. And so this I'll spend a bit more time today talking about. So this basic circle of ideas for Ricci flow. So first we have the so-called like smoothing effect for Ricci flow. So again, the statement I give here is not completely precise, but basically we say if the curvature is bounded by a constant k on some interval of this form, 0 to c over k, then on this interval, all the derivatives of curvature become bounded in this particular way. So t to the k over 2 times the norm of the kth derivative of the curvature tensor is bounded above by, is of the same size as this k, basically. And then using this smoothing effect, you can prove a basic obstruction to extending the flow. So again, the sort of loose statement for Ricci flow is if the maximal existence time for a solution is 0t, where t is finite, then you're sure that this should say that t is finite. Then you're sure that the curvature has to go to infinity at time capital T. So the Riemann curvature has to blow up at a singular time. And then another basic principle for the theory is compactness of solutions. So again, very roughly, what this says is that sequences of solutions with uniformly bounded curvature on compact subsets of spacetime and a uniform lower bound on the injectivity radius, again, you only need this at one point, but admit some subsequences which converge in the Cheeger-Gromov sense to a solution to Ricci flow. And so these basic tools together, you can derive a lot of natural corollaries about Ricci flow and sort of underlie all the more detailed regularity theory which follows. So I'm going to discuss sort of extensions of these and more today. And then, so I guess last time we did discuss a little bit of this general idea that curvature bounds torsion. So let me skip ahead to the main statement we gave. So we discussed maximum principle last time. And then, so I think this is more or less the last thing we covered. So the proposition is if we have a solution to generalized Ricci flow on some interval of the form 0 alpha over k, and on that interval, the curvature is bounded by k, then we get not just that the torsion is bounded, but we get sort of a smoothing effect for the torsion and its first derivative. So there exists a constant c depending only on n, such that for all times in that interval, the supremum of t times norm h squared is bounded above by this previous data, the constant depending on alpha. And then the same is true for t times the norm of the gradient of h. So the point being, like as long as the Riemann curvature is bounded, then the torsion sort of becomes in a sense, universally bounded in terms of the curvature. And yeah, I mean, so again, we discussed the proof last time, but it more or less boils down to maybe you can more or less the idea of the proof is visible just in this first line or maybe the second line. So this differential inequality says the time derivative of norm h squared is bounded above by the Laplacian minus twice norm grad h squared plus whatever constant is bounding the curvature times norm h squared, but then minus a certain constant 3/2n times norm h to the fourth. So the presence of this term is what allows you to get a maximum principal for t times norm h squared. So this is a very useful term. But in any case, yeah. So we discussed the details. It's just an elementary maximum principal argument last time. So okay, so yeah. Now we can go forward and discuss some more of these regularity results. In particular, like bounds on the higher derivatives of curvature and torsion. So I'll just begin by recording some basic formulas. So here's this lemma. It says if we have GT, a solution to generalized Ricci flow, then we have the following evolution equation. So if I apply the tensor heat operator to the Riemann curvature, then I get an expression like this on the right-hand side. So I get a certain quadratic term in the Riemann curvature. I get a term which is Riemann curvature times h squared, and then I get certain terms which are second derivatives of h squared. And again, all I mean by this is that it's some universal sort of quadratic contraction here between curvature and some universal contraction between Riemann and h squared, which of course is made explicit. I mean, we make this explicit in the book, but I don't bother here. And then there's a similar formula for the heat operator applied to the kth covariant derivative of curvature. So here we get this sort of awkward k plus second derivative of h squared term again. This is like this grad squared h squared term here. And then we get, again, certain universal contractions of sort of lower order derivatives, which look as follows. So the sum as j runs from 0 to k of the jth derivative of Riemann plus h squared times the k minus jth derivative of Riemann. And again, there's not much use, even in Ricci flow, there's not much use one makes out of really the precise form of this evolution equation for the derivatives of curvature. Of course, there's a lot that's done with the precise form of the curvature evolution itself, but nothing really is done with the precise form of the derivatives of curvature. So this kind of schematic formula is perhaps enough. And then, yeah, again, the proof is nothing beyond what is already known for Ricci flow, really. So this is a general fact that the evolution of the curvature tensor Rijkl will have as a leading order term this following combination of second derivatives of Ricci. And then there will also be, of course, a second derivative of h squared term. So in general, right, you get two derivatives of the variation of the metric. And so I just stuff the h squared term into this grad squared h squared. But then the second derivatives of Ricci end up looking like this. And then the point is you just use Bianchi identity. And then you can get that those actually magically reduce to the Laplacian of Riemann curvature. I say plus ... because there's lots of extra terms that are of these two kinds, Riemann squared or Riemann times h squared. Okay, so yeah, again, like the proof of this is just a standard thing, so I won't really say much about it. But I do want to just say a little bit about this formula for the evolution of curvature. I mean, yeah, so a really core concept in the study of Ricci flow is, of course, the preservation of these positive curvature conditions. And to be blunt, so far, nothing like this is known for generalized Ricci flow, and not even like a scalar quantity. So again, there's this famous fact that the scalar curvature is monotone. The minimum of scalar curvature is monotone increasing along a solution to Ricci flow. But there's not even like a scalar quantity which is known to have a preserved lower bound like this. And again, I just sort of maybe mentioned that almost certainly, like, first of all, the Riemann curvature is probably not really the right thing to study for this, almost certainly. Maybe bismuth, maybe some generalized curvature. And also maybe just using the standard Laplacian is probably also not, or potentially not really the right thing. You might have to use some delicate choice of Laplacian as well. And again, yeah, maybe it's more appropriate to use these sort of generalized curvature quantities coming from the theory of generalized connections. But in any case, I just, yeah, want to emphasize that this is sort of a core feature of Ricci flow that encodes a lot of really interesting geometry in various settings. And in any case, you don't know how to extend this to generalized Ricci flow. But there is sort of one exception, or one case that I'm not going to discuss today, but later, which is that we do have a sort of a Calabi type estimate for the generalized Ricci flow in complex geometry. And basically what this is, so Calabi shows how to get this C3 estimate for real and complex Monge-Ampere equations. And basically what he studies is he applies maximum principal arguments to essentially the connection coefficients of the associated metric. I mean, he doesn't exactly say that, but that's what he's, I mean, it's known that that's really what he's doing. And like in the study of like Kähler-Ricci flow, this is like the right quantity to study to get C3 estimates for Kähler-Ricci flow. And so in any case, there is a sort of extension of this, which is sort of, it's sort of loosely analogous to the scalar curvature monotonicity. It's sort of a quantity of the same order. But anyways, we'll come to that much later. But okay, so let me just state this basic smoothing theorem now. So if E is an exact Courant algebroid over a compact manifold, and then GT is a solution of generalized Ricci flow on a time interval of the form 0 to alpha over K, which satisfies the following bound. So here I assume a bit more than Riemann is bounded. I assume Riemann grad H and H squared are all bounded. Although with just a little bit more technical work, we sort of saw how the Riemann bound gives that these other quantities are bounded. In a sense, you can kind of drop these other two assumptions, but I'll just leave it for simplicity. Then the conclusion is that every higher order quantity is bounded in a certain sort of scale invariant way. So there exists, so given some constant K, there exists a constant depending on the dimension K and this extra parameter alpha, so that the kth derivative of Riemann curvature and the K plus first derivative of H, and then this kind of mixed quantity norm H times the kth derivative of H is bounded above by CK divided by T to the K over 2. And again, the sort of form of these estimates with this inverse T parameter is kind of predicted by just the sort of scaling law for generalized Ricci flow together with, well, yeah, it's basically just it's just the scaling law, which tells you the form of this. And again, like the sort of style of this estimate, it's like T equals 0 is sort of a boundary condition in a sense. And so we have a certain hypothesis on the boundary condition, but only about at the level of Riemann curvature grad H and H squared. And so we don't assume anything about the higher derivatives. And so this estimate necessarily has to sort of blow up at the boundary. It has to blow up at T equals 0. And indeed it does. Okay, so is the statement clear?
I'm a bit confused about so the right hand side depends on T, but on the left hand side you're taking the supremum over M cross the interval. So
yes. Sorry, that should say M cross T. Yeah, like it. Oh. This is like the data at time T. Sorry.
Oh, okay,
yeah.
okay.
I mean, I guess it's. I mean, it's probably true as stated, I guess, but well, maybe I have to think about that. No, it's not true, I guess. Yeah, sorry, that should be M cross T.
Okay,
yeah.
That makes sense.
Okay, so anyways, again, the proof is a fairly standard technique. And so I just very roughly sketched the case of k equals 1. So the point is to just apply the maximum principle to a certain test function. And given what you know you're trying to estimate, the form of it is not hard to guess, really. I'm basically trying to get a uniform estimate for t times this first derivative of Riemann and the second derivative of h squared. And as is often the case, you don't just want to bound this. You want to you sort of help yourself by bounding more. And of course, we already have an assumed bound for this quantity, norm Riem squared plus norm grad h squared. So it sort of doesn't hurt us to add this to our test function. But the point is, you can put together these previous computations to get the following differential inequality. And so you apply the heat operator to this f, and you're going to get certain nonlinear terms, for instance, which are of the form like curvature times grad Riemann squared. Those will be bounded by this CKT. But then, as we also saw, like in the evolution of Riemann squared, there's a good negative norm grad Riemann squared. And so that accounts for this minus p term. And then a similar phenomena happens for the Hessian h squared terms. And then there's just an overall kind of nonlinear term, which is certain powers of, described in terms of certain powers of curvature. And in any case, it's bounded by the following expression, Cp k cubed 1 plus tk. So in any case, this is all just coming from the assumed curvature bound. So of course, all these equations are nonlinear, like the equation for the derivative of curvature is nonlinear, but we're using this strong hypothesis of the curvature bound to sort of make it look more like a linear equation. But then, so when we use this upper bound on the time, and then you have to choose p, this constant p, large enough to sort of swamp this CKT term, and then you could do the same thing for this coefficient in front of the Hessian h, and you end up with a basic differential inequality that the heat operator applied to f is bounded above by ck cubed. And then it's just an elementary maximum principle applied to this. So then for small enough t, the supremum at time t of f is bounded above by the supremum of f at time 0 plus ck cubed t. It's just like a direct integration of the right-hand side up to time t. And then again, using the upper bound on t and the bound on the initial data. And of course, the key point, right, is that if the supremum of f at time 0 doesn't see, right, this term, right? At time 0, f is just bounded basically by the bound on curvature. I mean, I guess I could write a p there, but the p is chosen universally, so it's just some universal constant. And then and then that's it, right? So then the supremum of f at time t is bounded above by this constant c k squared 1 plus alpha, and then you just rearrange what that means, and it's exactly the case k equals 1 of the inequality we want. You have to take the square root at the end. So and like all the proofs, it's just more bookkeeping, I guess you'd say, for the higher k. But the idea is exactly the same. Okay. So with these estimates in mind, we can also prove a theorem similar to this curvature must blow up at a singular time theorem, which is stated as follows. So again, if E over M is an exact Courant algebroid, and again, I guess maybe I should assume M is compact. G naught is some generalized metric, and it has some, we let capital T be the maximal extended real number such that the solution to Ricci flow exists smoothly on this time interval, 0 to t. Then if this time is finite, so in other words, if it encounters a finite time singularity, then we can prove the following fact. So the lim sup as little t approaches big T of the sup norm of the Riemann curvature is infinite. Okay, so this is just loosely the curvature must blow up at a singularity. That's all it's saying. At a finite time singularity. And the proof is at this point a very elementary sort of extension of, or a very elementary application of what we already proved. So again, yeah, we suppose that T is finite, but that somehow the Riemann curvature is bounded, say, on all of M cross 0T. Well, I mean, using these smoothing estimates from before, if you just chop off a little bit of time and look at the time interval epsilon to T, then you have uniform estimates for h squared and grad h squared. That was from earlier. And then from this regularity theorem we just discussed, you have bounds on all derivatives of curvature and h. So you have sort of uniform estimates on all derivatives of curvature and h. Then basically you literally just integrate the generalized Ricci flow equation sort of as if it were an ODE. And you can define the metric at time capital T this way, and also like B at time capital T this way. You can define all the data at time T, and because all the derivatives of curvature are also bounded, it's just a straightforward argument to show that that limiting metric is actually smooth. It's again, it's one of these things that's a lot of bookkeeping, but there's not really an idea, I would say, beyond you just are simply integrating. And then yeah, so that's some smooth, so that defines some smooth, metric and three form at time capital T, and so we can apply the short time existence result to it. So the short time existence result tells us that at time T I can flow at least for some epsilon seconds, and once I do that, then I've produced a solution, a smooth solution to the equation on 0 to T plus epsilon, which contradicts the maximality of T. So, right, so the assumption was that somehow this was the longest solution of Ricci flow one could define. So yeah, again, this is a fairly standard argument.
Hi, Jeff, may I ask a question?
For sure, yeah.
Yeah, so in the Ricci case, there is this result of assume that it's enough to bound only the norm of Ricci tensor. And I know that the same thing is true for pluriclosed flow. Is there anything like that for generalized flow?
Yeah, so yeah, probably that's true. I mean, I don't, as far as I know, that's not been written down, but I guess the proof is just that you have, like, you have the uniform C0 equivalence, and then you use like volume comparison to show that like a blow-up limit has to be flat, I think.
Yeah, but there is a more straightforward argument by, I guess, Kochwar and Muntiano. They have another argument.
Yeah, but I guess that should be true probably, because.
Do you think Ricci will be enough, or you need something like
okay, yeah,
D star H?
Well, yeah, maybe it's interesting to work out, because, well, and when I say Ricci, I guess I mean generalized Ricci,
right?
Because I mean you want like the metric to be defined in C0 at the limit. So, but yeah, that's probably. In any case, it would be interesting to see. Yeah.
Okay. Thank
There's
you.
probably at least that much of a reduction of regularity. Yeah.
Hi, Jeff. Is there any? Is there any epsilon regularity if you work on, because in the Ricci flow case, if you work on the detect flow, I mean this is equivalent to Ricci flow, and you can basically we can recover this Sarsin result by epsilon regularity on the detect Ricci flow. Like if you have a metric G is epsilon close to some fixed metric, then you have all the regularity. Is there anything similar here? If this is true, then probably you just need to assume the generalized Ricci here to get the.
Sorry, the precise statement is just if the initial data is like C0 close to a known metric, then the flow exists. Is that the assumption?
Yeah. The precise statement is if you work on a detect flow, if the GT is epsilon close to fixed metrics for certain time, then you have all the regularity. This is about the Ricci detailed flow. Can you do the same things here? Can we do the same things here?
You probably, well, probably, I guess, probably, yeah, well, you probably want like that the generalized metric is C0 close to a baseline generalized metric, which somehow
Yeah,
encodes both G and B, I guess.
Yeah.
But
Okay.
yeah, that's probably true, yeah.
Okay.
I mean, in any case, it's very easy to believe that the proof would extend, yeah.
Okay. Okay.
But yeah, no, I'm not sure. That's good. Because I guess the proof is basically by blow up argument. You sort of blow up, and then you know you're sort of close to this. You have this like comparison metric which is flat, I guess. Is that the point?
Yeah, but yeah, I think you can even do it by hand, just by analysis, because if you work on the detailed flow, then you have sufficient parabolicity. Unlike this, yeah, because if you work on a detailed flow, but this is diffeomorphic to the original flow, then about the existence.
Oh, then yeah, probably that's. Yeah, that should work then, because yeah, I mean you have like uniform parabolicity bounds for this too once you have metric control like that. Yeah.
Okay.
So that's interesting. Okay. So yeah, we proved or at least discussed these like sort of smoothing estimates, and then this existence time obstruction. And now again, I'll just say a few words about the sort of compactness principle. And again, this is something that even though this is a learning seminar, you're not going to learn this here. But there's a lot sort of buried in this Cheeger-Gromov theory. But I'll sort of say what the relevant theorem is. And if you know how this Cheeger-Gromov topology works, it's easy to see how it will extend. But so let's just state the theorem anyways. So we say that a sequence of complete pointed generalized Riemannian manifolds converges in this C infinity generalized Cheeger-Gromov topology to some limit if the following holds. So I need an exhaustion of the limit M infinity by open sets UK, which each contain this O infinity, and some sequence of diffeomorphisms from UK to a set VK inside MK, which are covered, each of these diffeomorphisms is covered by some Courant algebroid automorphism FK, such that we have the following conditions. So first, phi k is identifying these origins. So that's this O is kind of like for origin. They're pointed solutions. You're fixing a point. And we require that this map identifies the origins. And then we ask that when you appropriately pull back the generalized metric from GK to a metric defined on an open set in M infinity, that this sequence will converge to the limit metric G infinity uniformly on compact subsets in the strongest possible topology. And this implies the sort of more classical fact that if you just pull back the underlying Riemannian metrics along the sequence, that those will converge to the limiting Riemannian metric in C infinity. And if you pull back the torsion 3 forms, that those will converge to the limiting torsion 3 form uniformly on compact sets in C infinity. So again, yeah, if for those who have never seen this, like a very basic example, I think I say it. Let me actually say note 2 first, perhaps. Like for instance, a really fundamental basic example that shows a bit how this works and how the topology can change is you can just take the sphere and then take the round metric multiplied by k and let k go to infinity, centered at the North Pole. Then I think hopefully fits your intuition to see that that converges just to the flat n space with the flat Euclidean metric, right? So as you scale the metric up, all the curvature quantities, the curvature of Sn is, getting smaller and smaller. The curvature is converging to 0. You look more and more flat on larger and larger sets. And when you make all that rigorous, it turns out that you're converging to Rn with the Euclidean metric. Sorry, I guess, and the example I wrote here, there's no Courant algebroid. It's just this is like classic example. But also the topology of this extra piece of topology coming from the Courant algebroid structure can change in there's, kind of trivial ways that it can change, where, for instance, you can just scale down your torsion 3 form. So I can just take a fixed, say, generalized Riemannian manifold, and then I can let HK be K inverse times some baseline H. And so, as you do this, obviously you're changing the real cohomology class of H as you do this. And in fact, you're converging to one with trivial H. I think that possibly, I think maybe there's something interesting deeper than obviously this example to be said topologically about how Courant algebroids can sort of change topology in this type of limit. But again,
is this related to your results about pretty close flow on compact complex surfaces, where you somehow have a Keller limit?
Yeah. Well, yeah, exactly. So I'll say like a few brief words about that. Yeah, this remains something mysterious for me, like something as trivial, maybe not as trivial, but as fundamental and basic as scaling is very strange in generalized geometry. It doesn't make sense really to scale a generalized metric. It's an endomorphism that squares to the identity. Whereas on the other hand, well, okay, you can scale G, and of course you can scale H. And so you can scale solutions to the flow. But as you do so, you're sort of changing this fundamental piece of structure, which is like the cohomology class of H. And indeed, there are cases where the right way to take a limit for generalized Ricci flow is to do what's called a blow down. So you're sort of scaling the flow at time t by 1 over t, and H as well by 1 over t, and then this converges to, yeah, like a Kähler limit, or just like an Einstein limit where H is naturally converging to 0. So I think somehow those simple examples are probably, it doesn't seem like it's hiding anything all that deep. You can just scale the H, okay, fine. But I think perhaps in these examples where there's like collapsing and stuff, maybe it's something more significant happening. It's just, in any case, it's always a strange thing that I guess even Mario mentioned something about this, that somehow the scaling laws don't work out well for generalized metrics somehow. Even though you can by hand obviously scale G and H in a geometrically meaningful way. In any case, let me just say a few words about this first note as well, which is just that the convergence is invariant under this enlarged Courant symmetry group. So what this means is I can just take like I can take, for instance, a fixed Courant algebroid and just pull it back by families of Courant automorphisms, and that's really just converging back to the original structure in this sense, because all I did was pull it back by this automorphism group. Or alternatively, you can think of it as if I have one sequence, EK, MK, GK, OK, converging to this limit, E infinity, etc., then I can pull the metric, the generalized metric, back by some arbitrary sequence of Courant automorphisms, and it still converges to this same limit. So in any case, the notion of convergence is, and again, this is a basic fact about Cheeger-Gromov convergence, which is just you can take any sequence of, if you have a convergent sequence of Riemannian manifolds, you can pull it back by an arbitrary sequence of diffeomorphisms, and you still converge to the same limit. It's a basic fact. So okay, yeah. So now let me just state the fundamental theorem of compactness for solutions to generalized Ricci flow. So again, here I have EK, MK, GKT, a sequence of complete solutions to generalized Ricci flow defined on some time intervals, which look like this. IK is alpha k comma omega k. And I suppose that the sort of initial times are converging to some time alpha, and the final times are converging to some limit omega. And I just assume uniform bounds on all derivatives of curvature and torsion. In all of space-time. And then I furthermore fix some origin OK in each MK, and some time in the limiting time interval alpha omega, and I suppose there exists a delta so that the injectivity radii of the kth metric at this time t naught at the origin point is bounded below by delta. So for all sufficiently large k, in any case, for basically for all k. So yeah, so the two key hypotheses are sort of uniform bounds on all these sort of geometric quantities, as well as a lower bound in the injectivity radius at one point in space-time, basically. Then there exists a subsequence of these solutions which converges to a pointed solution of generalized Ricci flow on this time interval alpha beta. And so, okay, on the last slide, I gave the definition of convergence of one metric, not a family of metrics, but it's a very easy extension to say what you mean by a one parameter, a converging family of one parameter families of metrics. So in this case, the one parameter families are generalized Ricci flows. So yeah, and again, this theorem is a not difficult extension of sort of the existing theory of Ricci flow, together with these like smoothing estimates and things that we already proved. But it is sort of long and technical. So like Hamilton's original paper proving the similar statement for Ricci flow is 40 some pages of estimates. But sort of you've already assumed very strong control over everything, so it's fairly maybe straightforward, but tedious thing. And I think this injectivity radius hypothesis is, of course, really crucial. So it's not hard to cook up examples of generalized Ricci flow or sequences of solutions which have sort of all these curvature type quantities bounded, but the injectivity radius goes to 0. And of course, when this happens, you can't expect to take a sort of meaningful limit, well, without sort of taking into account this sort of dimension reduction phenomena. So when you're losing the injectivity radius while the curvature is bounded, this is like under the theory of like collapsing manifolds. There's various ways to think about what happens on that lower dimensional space. But in any case, that's sort of beyond this theorem. Okay, so yeah, so those are the basic analytic tools for generalized Ricci flow, and I'm going to spend a bit of time saying a bit more about the like energy monotonicity that I guess Mario discussed to some extent, I guess, in his talks. But I'll say a few more words about how this works. So so we have these analytic tools, but we want to maybe use them to try to derive some corollaries about certain solutions of Ricci flow, or derive some qualitative behavior about generalized Ricci flow. So and the way we do that is with these energy and entropy functionals. So again, this is sort of a review, but let's just recall. So if I have Mn a smooth manifold, G a Riemannian metric, H a closed 3 form, and then a smooth function F, then I have this energy script F, GHF, which is the following. So this quantity, this R minus 1/12 norm H squared plus norm grad F squared, is kind of like this generalized scalar curvature that Mario mentioned, and then we integrate it against this density e to the minus F dV. And alternatively, for those who know like Ricci flow theory, of course, this is just Perelman's F in the case that H is 0. If you just set H to 0, this is Perelman's F function. And then we also define this quantity lambda. So lambda only depends on G and H, and it's the infimum over F's, which such that the integral of e to the minus f dv is 1 of the functional script f GHF. Okay, so it's a certain infimum over like unit volume f's in this sense. Okay, and then a basic lemma is that if you have a smooth compact Riemannian manifold with H as usual, then this infimum that defines lambda is uniquely achieved, and it's the lowest eigenvalue of this differential operator. So -4 Laplacian plus the scalar curvature minus 1/12 norm H squared. Okay, and then the basic fact, which I'm going to discuss, is basically that, and again, I think Mario already mentioned this in his talks, is that generalized Ricci flow is like the gradient flow of this quantity lambda. And the proof of that is based on like a series of, well, like a family, if you will, of monotonicity formulas for this script f, basically. Okay, so here's a basic lemma. So if I have a smooth manifold and then one parameter family is a GS, HS, FS, whose variation at time 0 is as follows. So the variation of G is little h, the variation of H is dk, and the variation of F is phi. Then I get the following variational formula for script f. So the derivative of script f at time 0 is the following. So integrated against the variation of the metric is minus Ricci plus 1/4 h squared minus Hessian f. Integrated against k is minus 1/2 d star h minus grad f left hook h. And then we have this sort of slightly mysterious extra term, which is this certain density r minus 1/12 norm h squared plus twice Laplace f minus norm grad f squared integrated against 1/2 the trace of h minus phi. And then all of that is integrated against the e to the minus f dv. And so it sort of suggests, if we wanted to study, say, the gradient flow of this quantity. So suppose we didn't know anything about generalized Ricci flow or whatever, and we wanted to just study the gradient flow of this script f. Well, you can see it sort of suggests a slightly different equation, right? So it suggests that if we had some family f of t, then the gradient flow ought to be this sort of gauge fixed generalized Ricci flow. Okay, so here I wrote this is the generalized Ricci flow system, but then modified by these two gauge terms. So this minus twice Hessian f we would recognize as the Lie derivative of the metric with respect to grad f. And actually, I guess if I was, there's again something perhaps mildly mysterious here, which is that this grad f left hook h is of course not quite a gauge term. Once you take the exterior derivative of this, then it will be the Lie derivative with respect to grad f of h. But it's kind of missing an exact term. But nonetheless, we can interpret this as a gauge fixed generalized Ricci flow. Well, so that's one thing, is that looking at this formula, it seems to suggest a sort of studying a gauge fixed flow, but also, of course, we need some kind of PDE for f, or some kind of equation in any case for f. And we also have this last term to deal with. And the sort of magic of Perelman's argument is that these problems all kind of fit together and resolve each other simultaneously. So yeah, so if we're going to prove that generalized Ricci flow is or this gauge fixed generalized Ricci flow is the gradient flow of lambda, then we end up proving this sort of family of monotonicity formulas for script f, which requires coupling to some evolution equation for f. So what is this relevant evolution equation? So if we have a solution to generalized Ricci flow, we can say that a one parameter family of functions ut, and I deliberately chose u, not f, for a reason which will become clear, is a solution to the conjugate heat equation if the following holds. So 0 is box star u, which is minus ddt minus Laplacian plus the scalar curvature minus 1/4 norm h squared times u. Now, the reason for picking this equation, well, there are perhaps several reasons, but the main thing is that it's the L2 adjoint of the time-dependent heat operator. So because the volume form is changing along the flow, the heat operator is not self-adjoint, right? And so this is the or it's not a joint to the backwards heat operator. It's a joint to this operator, this box star, because the volume form is also changing. And in fact, it follows directly, this is just the same circle of ideas, that the time derivative of the L1 norm of U measured against the moving background is 0. And again, this is just sort of the presence of this extra scalar curvature minus 1/4 h squared exactly cancels out the term arising from the variation of the volume form. And so what that means is that if we interpret, if we define f by e to the minus f equals u, then this PDE will give us a family of valid test functions for lambda, right? So it's preserving this like unit density condition that's required for lambda, right? So like when we define lambda, we take an infimum not over all f's, but of these special like unit density f's. And so this family ft will preserve that condition.
The identity that you wrote holds without the integral, right? So the derivative of ut dvt is also or not, or is up to.
No, I guess it will equal Laplacian ut dvg, I guess.
Oh, okay.
Yeah, which integrates to 0. So it's a pure divergence. Yeah. So let's see how to use this. So again, if we have a solution to generalized Ricci flow, and then we define ft as follows: e to the minus ft equals ut is a solution to the conjugate heat equation as before, then we claim the following monotonicity formula. So we claim the time evolution of script f is twice norm Ricci minus 1/4 h squared plus Hessian f squared, and then plus 1/2 norm d star h plus grad f left hook h squared. Again, measured against the sort of relevant moving density there. And so what's the proof? Well, there's something sort of kind of magical that happens. So notice I claimed this generalized Ricci flow, not the gauge fixed one, which we sort of mentioned before. But what you do is you sort of say, well, okay, I have my solution to generalized Ricci flow. If I pick a density u at some forward time, then I can solve this backwards heat equation back to the initial time. That will define u for me and thus f. And then I can pull all of that, the metric h and f, back by the diffeomorphisms generated by grad f. And then you get a solution to the following equation. So you get, you get this gauge modified, you get this gauge fixed generalized Ricci flow, which here I guess I wrote at the level of h for some reason. And then f, so I didn't write down the evolution of f before, just u, but it's easy to derive the evolution of f based on this relationship, e to the minus f equals u. And when you pull it back by the relevant diffeomorphisms, this is the equation you get. So df dt is minus Laplace f minus r plus 1/4 norm h squared. And it took me a long time to, I mean, I think these formulas are sort of relatively easy to derive, but it took me a while to really appreciate the sort of analytic miracle of this, which is, you know, at first glance, you look at this system and it seems to be a coupled second order system, even just forget h, just even in the case of Ricci flow. It's a coupled second order system where one equation is forwards parabolic and one equation is backwards parabolic. So under almost any circumstance, this is completely garbage. You'll never solve this. But of course, the point is that the coupling, that the equations decouple, because the sort of presence of Hessian f here is exactly this Lie derivative term. So this system can be solved in exactly the way I said. You just start with the generalized Ricci flow, then you define the u and thus the f, and then you pull it all back, and then you solve this system. And then the sort of further kind of magical key point is that just by examining this system, you can see that you have 1/2 the trace of dg dt minus df dt is 0. So this was exactly the coefficient in front of this extra density in the variation. So I mean, maybe I just quickly jump back. So if you look at the calculation, basically this is exactly sort of arising from the variation of the volume form, of this moving volume form. And so basically, because we're preserving the unit mass, that term ends up dropping out, at least for this gauge fixed version. And then I guess the last thing that we're exploiting, which I didn't explicitly mention, is just the diffeomorphism invariance of script f. So it suffices to prove to prove this evolution for the gauge fixed flow, as opposed to the standard flow. So yeah, I don't know. Are any questions about that? I don't know if it's too fast or.
So this invariance of the volume occurs in the after gauge fixing or for the original?
So yeah, there is a subtlety, right? So the integral, I mean, yeah, the volume is preserved when you have like a generalized Ricci flow and then a solution of the conjugate heat equation. But then when you properly gauge fix, then the volume form is preserved. Yeah, and that difference is, of course, yeah, that's necessary, or I mean, that's used. Yeah. Yeah.
Is it parallel with the steady soliton, steady case in the Ricci flow?
Sorry, is what parallel?
Is the entropy here, the F entropy here, parallel with the steady case in Ricci flow?
So steady Ricci solitons will be, well, I mean, yeah, in the compact case it's already Einstein, but they will be fixed points for this. Is that what you're asking?
Yeah.
Or,
is there any similar entropy in the shrinking case? I mean, is there analog here?
I was gonna say, as long as, I mean, I guess lately we've been going beyond 2 o'clock, and yeah, I mean, I was gonna say a few words about that, not a lot, but yeah, the short answer is yes, there are. So yeah, so let me just briefly say how to actually prove this energy monotonicity. You say, suppose M is compact and you have a solution to generalized Ricci flow. Then for all times t1 less than t2, you have that lambda at time t1 is less than lambda at time t2. And equality holds if and only if you're a steady generalized Ricci soliton. Okay, and again, the proof is kind of like what I said already. So you choose F2, so you choose F at this final time t2, which realizes the infimum there at time t2. And then since M is compact, we can solve this conjugate heat equation with the final time boundary condition, right? So again, this conjugate heat equation is a backwards parabolic equation. So we fix this final time data and then solve on the interval t1, t2. And then it's just the following sort of trivial sequence of inequalities. So lambda at time t1 is of course less than the value for any valid test function f. And because of this preservation of unit volume, ft1 is a valid test function. And then just using the monotonicity formula for f, that'll be the value at t2 minus this time integral of this relevant density. And then by construction, script f with respect to this little ft2 is just giving us lambda at time t2. And then so finally we get lambda at time t1 less or equal to lambda at time t2 minus this relevant quantity. And so all the statements sort of instantly follow from this. Okay. So yeah, so let me say, I didn't really plan to get too deep into this, but I just want to say a few words about the expander and shrinker cases. Again, this might seem quite mysterious if you've never seen it before. I think Mario's.
Yeah, can you go back to slides?
Yeah.
Back.
Oh, again?
Yeah, another one. Yeah, it's just for this. I was thinking about the interpretation of the proof. Like in this new gauge, what you are doing is like fixing the divergence, and then your F appears naturally. Your F is just the difference between the Riemannian volume and some fixed volume that you have fixed.
Yeah. Yeah, I think that's right. Yeah.
And then and then you are solving this gauge fixed. I mean, yeah, this generalized Ricci flow with divergence, and then after engaging, you get the statement of the proposition. But my point is that in the other gauge, in the gauge of the proof, what you are doing is just fixing a divergence and flowing the generalized Ricci flow in that fixed gauge for that divergence.
Yes, that's true. Yeah. Oh, I see your point. Yeah.
Anyway. Sorry.
Yeah, no, that's interesting. Yeah. So let me define this so-called expander entropy. So again, we have our usual data G and H, and now I fix a density U and a positive number sigma, and then I define F plus as follows. So F plus is implicitly defined by this relation. So U is now e to the minus F plus divided by 4 pi sigma to the n/2. And the form of this is kind of suggested by like heat kernel asymptotics, as we'll sort of kind of see. But then you can define an expanding entropy associated to this data. So it looks like W plus GHF plus sigma is the following integral. So it's fairly similar to the energy, but now the density or the sort of curvature part is weighted by this constant sigma. And then there's this extra term involving F plus here. And then the whole thing is integrated against this function U, which again is not quite e to the minus F anymore. So in any case, there's all manner of sort of explanations maybe for this quantity using like these Nash entropy and things like this, and coming from, like I said, analysis of heat kernels. But let me just state the result. So if we have a solution to generalized Ricci flow, and then again, this UT will be a solution to the conjugate heat equation. And then I define FT as follows. So I fix this parameter sigma to be little t minus some initial time. So here, actually, capital T is more like the initial time. You could take this capital T to be like 0 if you want to. It's just some like initial time. And then little t is bigger than capital T here. So this is a positive number. Then we have the following monotonicity formula. So the time derivative of this W plus along the flow, where this sigma is little t minus big T, looks as follows. So it's this sum of 3 terms. And how are these to be interpreted? So remember, this little t minus big T is positive. And so this quantity here is sort of like the norm squared of what ought to be like this kind of expanding soliton equation. So like, for instance, this is 0 if H is 0, F is constant, and Ricci is negative G. Okay. So like, for instance, this first term here would be, is constant, or is 0 on a negative constant Einstein metric. But then we see actually the same term involving D star H as what showed up in the energy calculation. And then there's this kind of anomalous extra 1/6 norm H squared term, which is positive. All of that integrated against U. So this turns out to be a useful monotonicity formula. And again, since someone sort of asked, I'll say a few more words at the end, but like, this is how you prove, it's with this formula that you can prove these sort of like rigidity results for certain blowdown limits of generalized Ricci flow. Basically, because of this extra norm H squared term, you expect H to go to 0 on certain blowdown limits. As long as things converge nicely enough. And then, yeah, so there's also a shrinker entropy. So so again, like these quantities, they're all extensions of the things Perelman defined in his first paper. And the shrinker entropy for Perelman is the most important because it's the one that gives you this kappa non-collapsing result. So again, I'll say some words about that. But it's a very similar construction. So we have our usual data, G and H, and we have a positive function U. And yeah, I guess tau is a positive constant. And we define F minus very similar to the way we defined it before for the expander entropy. So U is e to the minus F minus over 4 pi tau to the n over 2. And then we define this shrinker entropy, which again, it looks really similar to the expander entropy. It's just that the signs on this F minus and the n term have changed. Okay, so the signs on these terms have changed. But in any case, what the proposition says is now I take a solution of generalized Ricci flow on a compact manifold, and then I interpret tau. Now it's capital T minus T. So now capital T, tau is basically the time until a singularity, you imagine. So capital T is maybe the singular time, and then tau is how many seconds left before the singularity, basically. Then you get the following not quite monotonicity formula. So the time derivative of this W minus entropy with all of this data is as follows. So again, it's the integral over m of 2 tau. And then here I get this certain quantity, Ricci minus 1/4 h squared plus Hessian F minus 1 over 2 tau g. Again, this quantity, for instance, is 0 if h is 0 and g is a positive constant Einstein metric or a shrinking Ricci soliton. Okay, and then again, we get this same d star h term, but then the sort of unfortunate part is that we get this extra norm h squared term, but it has the wrong sign. And again, this is something which is difficult for me to decide what the meaning of this is, because well, for one thing, it prevents you from immediately obtaining corollaries. I mean, the W is simply not monotone, not in general. And so there's sort of an obstruction to obtaining natural corollaries. And I think it's possible that this, in any case, there are various possible meanings. Like it's possible that you need to study something slightly different from the conjugate heat equation. So this is something that Mario and I discussed. Like maybe the U has to evolve by something slightly different to still get a useful entropy type monotonicity formula. I think this is one possibility. But on the other hand, I think I'll say something about this on the last slide. You can actually kind of fix this term by assuming some extra structure, which you basically always have for the complex versions of this flow. So you can sort of recover this shrinker monotonicity for the complex versions of this flow for pluriclosed and generalized Kähler. So again, it's a little bit remains a bit mysterious to me, because again, we sort of do expect. I mean, you can even prove that the only natural notions of sort of shrinking soliton for this generalized Ricci flow equation instantly imply that H is 0. So you sort of still expect this sort of strong rigidity of shrinking solitons, that they should just be classical solitons. But in any case, for those that like to play with entropy functionals, I invite you to fix this problem. But we discuss it more in detail in the book. So yeah, so let me just end by discussing a few natural applications of these energy and entropy formulas, which sort of, again, the proofs are sort of standard proofs, and you can look in the book. We discuss these results, but sort of building on these monotone quantities together with this basic analytic structure theory, you can derive some nice corollaries. So for instance, again, I make a sort of rough statement. I say non-singular solutions with bounded geometry. So what do I mean by that? So just assume you have a solution of generalized Ricci flow that exists for all time, and the curvature is bounded, and the injectivity radius is bounded below, and the diameter is bounded above, say. Or you don't even need the diameter assumption, I suppose. then you can prove that as time goes to infinity, it will converge to a steady soliton. And again, this follows in a standard way from using this lambda functional. So basically the lambda is increasing, and because you have the bounded geometry, it's bounded above, so it basically has to converge to some limit at infinity, and that means that it has to be limiting to a soliton. And in fact, this was more or less the line of reasoning I used to predict the existence of non-trivial solitons on these type 1 Hopf surfaces. So again, this is something we'll get to eventually, but like we discussed this example of S3 cross S1, which is just a fixed point for generalized Ricci flow. But well, in any case, again, we haven't gotten to the complex case yet, but like for generalized Ricci flow in the complex setting, for different complex structures on the Hopf surface, you know you do not have this actual fixed point, but nonetheless, the sort of natural conjectures about generalized Ricci flow say that the solution ought to be non-singular in this way, and so it ought to converge to a soliton. And so, inspired by that, we looked for them and found them. This is like work that I did, and then later Yuri and I sort of built on it. And also, so using this expander entropy, you can prove that solutions with non-singular blowdown limits. So again, what does this mean? Basically, you have a solution defined for all time, and then you look at like gt over t. So if you take the time t data and divide it all by t, and also you take ht and divide by t, if that sort of has uniform estimates, uniform geometric estimates in the same way as what I said before, then using this expander entropy, you can prove it's converging to a negative scalar curvature Einstein metric. So again, you get this strong rigidity, right? It's not like generalized Einstein in some way. H is just 0. It's classically Einstein. And that's following, like I said, from this extra positive norm H squared term in the expander entropy. And then also, yeah, so I sort of already said this, but just say a bit more. So if you have this extra piece of structure, we describe this in the book called a torsion bounding subsolution. So it's just a certain kind of nice function along the flow. This is definitely some extra hypothesis, but you sort of always have it in the case of pluriclosed flow. Then you can fix this expander entropy, and you can reprove, not reprove, you can extend this Perelman's kappa non-collapsing to the setting of generalized Ricci flow, or at least pluriclosed flow. And again, you can also prove strong rigidity of sort of non-singular, like type 1 so-called blow-up limit. So if you have a finite time singularity and you do a natural rescaling and you get sort of strong uniform convergence, then it has to be to not just a soliton, but a classic shrinking Ricci soliton. So H again will be 0 in that setting. So yeah, so that's it. And I guess yeah, any questions as we end? So yeah, I mean, thanks for all the questions earlier. That's some interesting ideas. This is exactly the kind of thing I had hoped would come out of this. Yeah, like I think extending these various things you guys mentioned in terms of the regularity, I think is quite interesting. So yeah, I guess if no questions.
I'm sorry, I have a question.
Oh yeah,
So
please.
does it mean the shrinking case, in the shrinking case, there is no rigidity? Is that it?
No. Like yeah, like basically any natural notion of shrinking soliton, and I think there's maybe kind of some competing notions, but they all sort of imply that H is 0 if it's compact.
Okay.
And again, using this kind of argument that I just very loosely indicated, like when you do have this so-called torsion bounding subsolution, then you can flat out prove that like these limits are classically shrinking solitons.
But you are not using the entropy. You are using something else.
No, well, what I guess maybe it's a bit too vague. So So this W minus, of course, is not monotone.
Yep.
But my claim is that if you include so when I say this torsion bounding subsolution, what I mean is you have like a bounded function such that the heat operator is bounded above by minus norm h squared. It's just it's a technical device, but the point is that it does exist, at least locally in the pluriclosed flow setting, and in lots of cases globally. And so if you have this, then you can basically modify this entropy using this extra function. In fact, when I wrote my notes, I left a typo. This phi is supposed to be this extra torsion bounding subsolution. I meant to delete that, but you can basically add, you include this extra special function phi into the density, into this W minus, and you get a monotonicity formula just like this proposition, but you can flip the sign on the norm h squared term.
Oh, okay, I see.
So you recover, like, you know, not only the monotonicity but the rigidity as well.
Okay. Okay. But in general, we can't do it.
Yeah, right. So yeah, right. And so this trick, yeah, you can basically always make it work in the complex setting. But yeah, for the actual generalized Ricci flow, this remains for me. I mean, and almost certainly this trick, I mean, I don't know, you can recover a lot of analysis out of it, but it's not very geometrically meaningful. I mean, I very much think that there's a nice geometric idea hidden somewhere that somehow in a way this is not quite the right entropy functional, even though it can give results, and that somehow even the expanding one, even though it gives a strong result with an extra positive term, is maybe in some sense not quite the right one. Because somehow these norm h squared terms should not be there, and it's either the wrong entropy or we're using it wrong or something, and maybe we have to change the conjugate heat equation or something.
Why you're saying that this is not the correct, seems to be not a correct notion?
Well, it strikes me as so strange that when you do this expanding one, you just get this weird extra term that just comes out, this extra norm h squared that just pops out, that happens to have a good sign in the expanding case and happens to have a bad sign in the shrinking case.
Okay.
Whereas, you know, the same general circle of ideas and the same like using the conjugate heat equation, and the same gives, you know, sort of a really sharp, clearly relevant result for lambda. I mean, like, these solitons really do exist. I mean, actually, I should have emphasized that and I didn't, right? So it's this well-known fact that, like, compact, steady, classic Ricci solitons are just Einstein, right? The F is 0, a constant, the F is constant. But that's not the case here, actually. There are genuine solitons where F is not 0. So, I mean, like, this functional, this F functional is really capturing something that genuinely is happening with generalized Ricci flow. And I mean, the W plus is, but it's sort of, somehow this 1/6 norm h squared wouldn't bother me if it didn't show up in the wrong way in this one. This is what makes me think that somehow an idea is missing. Or it could just be an analytic difficulty. I don't know.
Okay.
Yeah.
Okay, thank you.
Sure. Anything else? Okay, yeah. Thanks, everyone. Thanks for coming. And I guess we'll actually, maybe since you're all here, maybe I mentioned, I sort of considered that perhaps this should be our last talk of the quarter. Maybe we take a few weeks break, because I think basically at this point we want to switch over to complex geometry. And Marco had agreed to give some talks on generalized complex geometry. So maybe we give him a bit more time to prepare, since I sprung it on him a little bit. And maybe if it's okay with you guys, we start again in the new year, and I'll send out another, like, organizational email so we can figure out when to meet, because I imagine everyone's schedule is changing. I don't know, Mario, you think, is it okay? Yeah. Okay. But yeah, okay, thanks everyone.